Dr. Parthasarthi Wangipudi is presently working as an associate professor in the Department of ECE at Amity School of Engineering and Technology, Amity University, India. Dr. Parthasarthi's research interests include working on computer vision algorithms, medical image analysis, and development of medical image retrieval platforms. He has taught undergraduate courses in image and video processing and supervised several undergraduate students in research. He is currently also a co-principal investigator for two ongoing research projects sponsored by Department of Science and Technology, Government of India. Welcome once again, sir. We're honored to have you grace SPIN 2025.
टाइम लगाओ ना फिर लगाओ अब शेयर कर लोगे हाँ शेयर ठीक नेक्स्ट है 471 एक सेकंड और this one 195
Yes. Please carry forward.
Ma'am, shall I start?
Yes, yes, please start.
Okay, greetings everyone. Myself Mehakpreet Kaur from IGDTU and I'm pursuing BTech Computer Science with AI. So the topic of my paper is VGGNet plus a novel approach to image-based facial recognition. So as we know, we humans have the ability to recognize faces even after long times and even in harsh conditions like blurriness. So the current work enhances the VGNet 16 convolutional based with 3 customized layers for facial recognition on the face of dataset. The model addresses challenges of limited training data, subject distance, and lighting variations. Anomaly detection is incorporated to identify unauthorized or unknown subjects using the isolation forest technique. The proposed system achieves 97.5% recognition accuracy for known subjects and zero misclassification for the unknown subjects. So the challenges we usually face in this domain are variation in illumination, pose variability, occlusions, facial expressions, low resolution and blurry images, background clutter, and variability. So this paper tries to address some of these issues. The motivation behind this paper is the growing demand for the automated systems in security, forensics, and defense, and advancements in deep learning, CNNs, VGGNet, effective detection of unknown subjects critical for security applications. So the proposed structure of the VGGNet Plus is shown on the screen. The initial layers of the VGGNet 16 are similar, but some modifications have been done in the later layers and some additions have also been done. The architecture is as follows. So we have used MTCNN for face extraction and detection. Then we have used VGGNet 16 with some custom layers, and then we have combined and extracted the embeddings which we have been used in the training of isolation forest for anomaly detection. Then we have testing and prediction of known unknown faces, and a performance evaluation has been done using a confusion matrix. So why we have used VGGNet is as compared to all the popular architecture like FaceNet, Inception, and ResNet. So given the data set and the quantity and quality of the data set, VGGNet has a lower computational complexity, and despite its parameter count, especially on standard data set. So talking about the dataset we have used, it's the FaceUp dataset, which includes 460 videos frames featuring 252 subjects. So the videos were recorded 36 feet from the camera. And there are many locations, like 3 in outdoor and 1 indoor, with various lighting settings. The flow chart is, so first we have added some layers in the VGG16 model. We have added a flattened layer, a dense layer, then a dropout layer. So these are the modifications we have done. Then we have extracted the embeddings from the test set, which have been used for calculating the anomaly scores for the test embeddings in the isolation forest technique. So talking about the anomaly detection, isolation forest technique, why we have used this. So the most of the models fail to detect anomalies or unauthorized subjects. Isolation forest technique is integrated for anomaly detection. The embeddings that are extracted from the dense layer are used as input to the isolation forest algorithm for anomaly detection. This technique makes use of decision tree to efficiently isolate anomalies by randomly selecting features and splitting data based on threshold values. So the results are, as we can see, the model has correctly predicted with a high percentage. It has given the label for the person which the model has detected, and the confusion matrix is also presented. So the performance highlights are 97.5 accuracy achieved for known subjects and 0 misclassification for unknown subjects. And the future scope, we are working on optimizing it for large scale, real scale deployment. Thank you.
Any queries?
Thank you.
I would request paper ID 471 to present his or her paper. Can I see your ID?
So 47, this one, yeah. You can control it.
Okay. So good afternoon, everyone. Myself Karthik Garg, and I'm going to present the paper Advancing Transfer Learning with Gap, Depth-Wise Constraint, and Average Depth-Wise Constraint for Diverse Datasets. This particular research is currently regarding the image classification problem. As we all know, deep learning is when we do deep learning projects, we basically need large datasets. But to solve that particular problem, we use transfer learning, in which there are certain predefined models which are currently having some large dense layers, and they have a lot of number of parameters and everything. So we train our small dataset on those particular pre-trained models. So in this particular research paper, we use 3 different layers: gap layer, depth-wise constraint layer, and average depth-wise constraint layer, to remove the problem which we face normally, is that when we apply transfer learning directly without any custom layers, the accuracy is sometimes very low. So it's a global average pooling layer. So this is the datasets used. I use 2 different datasets. One of them is Intel image dataset, and another one is MIT indoor dataset. Both of the datasets are publicly available on Kaggle. The Intel image dataset consists of 6,000 images and 6 different classes: buildings, forests, glaciers, mountains, seas, streets, etc. The standard image size of the Intel image is 150 cross 150, but I resized it to 224 by 224 pixels. On the other hand, MIT indoor dataset consists of 67 indoor scenes, means 67 different classes, and their total amount of images are 15,620. The image size for the MIT indoor dataset is variable. Each image is of different size. So I rescaled it to a particular number, which is 512 into 512 pixels. So model architecture and tool use are, I used 5 different pre-trained models: Tensor169, Resonant50, EfficientNet V0, MobileNet V2, and ExceptionNet. The model architecture which I used, as I mentioned earlier, I used 3 different custom layers: global average pooling, depth constraint, average depth constraint layer, and the tools used are TensorFlow, Keras, and I use a Kaggle environment for this particular problem. In that particular problem, I use the GPU of Tesla P100 GPU, which is publicly available on Kaggle, and it is free for 30 hours per week. And I use certain matplotlib C1 technology for visualization. This is a basic model architecture. First of all, I input the data, and then I did some pre-processing like image augmentation, in which I did zooming, rescaling, resizing, shifting, tilting, all these kind of things. After that, I chose the model. As I mentioned earlier, there were 5 different models: Session2, ResNet, ExceptionNet, MobileNet, and EfficientNet. And then I applied 3 custom layers, one for each model. So in this particular way, I trained total of 30 different models, 15 for each different datasets. The training setups of hyperparameters I used was stochastic gradient descent with a momentum of 0.9, learning rate of exponential decay, batch size of 70 for MIT dataset, and 15 for batch size of 15 for MIT dataset and 70 for Intel image dataset. Epochs, I use different epochs for MIT and Intel also. For Intel dataset, the epochs are 220, and for MIT it was 130. The computational environment, as I mentioned earlier, was done on Kaggle notebook. So these are the basic results. As you can see, in the TestNet169, average depth constraint model gave us an accuracy of 87.3%, whereas the global average pool layer gave us an accuracy of 84.5%. On the other hand, it gave us a higher sensitivity and a specific gain also, which is much more higher than the other layers. Same goes for efficient net B0. The accuracy goes for 88.3% with the average depth constraint, outperforming gap layer. Similarly, precision boost is 89.1%, top one accuracy is 99.9%, and most efficient model. It is the most efficient model because the parameters are much less, which is 4.09 millions only. This is the performance table which I created. As you can see, it consists of all the results on the test dataset which we have from the MIT and the Intel image dataset. It has all kind of parameters which we can see: test loss, test accuracy, precision, recall, top 1 accuracy, top 5 accuracy, F1 score, sensitivity and specificity, and also the parameters. So as you can see also here that EfficientNet has the second lowest number of parameters, followed by MobileNet, which has the least number of parameters. This is the accuracy comparison for gap layer and depth-wise constraint layer. As you can see, depth-wise constraint layer outperformed at every model for the gap layer. And this is a parameter efficiency graph. It shows that what were the different number of parameters for different number of models which we chose. As you can see, MobileNet has the least number of parameters, then EfficientNet, then we had TensorNet, and after that we have ExceptionNet, and at last ResNet with the most number of parameters. These are the results for MIT indoor dataset. As you can see, average depth constraint gives us an accuracy of 60%. And again, this accuracy is very low, but it outperformed the accuracy of gap layer, which is 30.6%. The basic reason behind this level of accuracy is that the image pixels, as I mentioned earlier, were 512, 512, which lead to a bigger image size, thus lead to the less number of lower accuracy. But on the other hand, if you can see, the EfficientNet model gives us an accuracy of 71.3%. And ResNet gave us an accuracy of 58.7. MobileNet gave us an accuracy of 52.4. And the best model was by ExceptionNet, which gave us an accuracy of 71.6% by the depth-wise constraint layer. This is the comparison graph for gap layer and the depth constraint layer. As you can see, the exception model, as you can see, the gap layer didn't perform much well. The accuracy was nearly 0. On the other hand, the depth constraint layer gave us a higher accuracy of 71.6%, as I mentioned earlier. This is the performance table. These are the key insights. The device constraint improves accuracy, especially on high resolution images. And efficient, we will achieve the best balance of accuracy and efficiency. Exception and ResNet shows higher sensitivity to device constraints. These are the key conclusions. Device constraint perform better than the gap layer in every term. And for the future work, we are focusing to use these models for the medical imaging and AI in different kind of fields. These are the references which I use. I used a total of 15 different references, which along with 2 different data sets which I used. Thank you.
Thank you. Please just tell me, like I didn't get what are those layers, the custom layers that you added and why you are adding?
So, sir, I did 3 custom layers.
Right.
A global average pooling, device constraint. Actually, sir, I didn't created a proper layered architecture for that. I added these layers at the end before flattening the complete layers.
What do you mean by depth constraint?
Uh,
What do you mean by depth constraint or average depth constraint?
Okay, sir. So as we know, in global average pooling layer, it takes a global average of all the spatial information which it has.
All that?
Informations or the pixel information, the spatial information the layer has, it just take a global average of that. So that particular layer leads to the loss of information or much of the spatial information. But when we go to depth-wise constraints, in that particular region, it just basically focuses on reducing the complexity of the model. It doesn't focus on reduce.
How does it reduce the complexity of the model? What is the constraint? Depth constraint, what do you mean by that?
So in that was constraint, according to my knowledge, I may be wrong about that. The layer which I included in the model, it may be taking the less important features and taking it may be taking the layers and then doing some depth first constraint like looking upon different type of features it has and only extracting the main features from it, not taking the average, but taking the major and basic features which is important and required in the model in the later terms.
You need to, since you're talking about the custom layers,
Sure.
right? So you need to have extreme clarity about why you're choosing them and what you're doing, right? So that is one. Second thing, if you go to the slides, you have said that you have scaled the input size to 512 cross 512. This has been scaled to 224 cross 224. Sure. But then every CNN has a specific input size.
Yes, sir.
So, how come you are sending it this 224 by 224 images to all kinds of networks?
Sir,
And
while
how come you are sending it the same size, different size to all the networks?
if I may, sir, while I was doing this particular thing, I came across the same issue which you mentioned here. While I was directly inputting the image size of 150, 150, there was an issue that the image size is not compatible. So while I saw different kind of models, and then I chose 224, 224. It has a standard size. It worked with all 5 models. So for the Intel image, I went with that one. Then I went to MIT indoor dataset and I rescaled it to 512, 512. It didn't show any problem with me while I was doing it.
You have a standard input size. The dimension is going, for example, for AlexNet, it will be 2.4 plus 2.4. For ResNet, it would be something else. It would be a standard dimension.
Yes, a standard dimension for that's why I scaled Intel image to that only. But for MIT indoor, I thought that I should be extended much more further. So I tried to directly importing that image into the model, but it didn't show any error to me. It worked fine. So
Is it a multi-class classification?
yes, sir.
Huh?
Yes, sir. There were 67 different classes.
Any other questions?
Thank you.
Thank you.
Now paper ID 484, which is identification proof. 484.
Just take
Is it there?
Yes,
Hello. 44.
Yes.
Yes, I have to present 484.
Like,
I
can
have to
you?
present online.
Yes, ma'am. Yes, ma'am. Okay. Can you just show your verification ID?
Yes, definitely.
Yeah.
I am unable to share my screen. Can you just enable it?
Yeah, one second, one second.
I hope my screen is visible.
Yes, sir, it's visible, sir.
This is my ID. I hope my ID is visible.
Yes, sir, it's visible, sir. Sir, can you proceed with your papers?
Yes.
Yes.
Shall I share it?
Yes, sir. Yes, sir. Vipul Chandra Vasu.
Shall I start? Shall I start? Am I audible? I cannot hear you. I cannot hear you.
So you can start now.
Okay. Good afternoon to all of you. Myself, Vipul Chandra Vashne, and I'm here to present my paper titled Astro LSTM, a model for stock market analysis using astrological features. So these are the contents I am going to present. That will be introduction, research motivation, astrology and machine learning, research contribution, dataset collection, proposed method, results, conclusion, future scope, and the references. Basically, this is an interdisciplinary approach combining the traditional astrology and the modern machine learning. And specifically in astrology also, we have covered a branch of astrology that is financial astrology and its role in stock market. And basically, the financial astrology deals with the movements of celestial body. Further, we have proposed a model that is Astro LSTM, which is a novel model which to analyze the relationship between the planetary declination and the stock market movements using the LSTM network. If we talk about the research motivation, so basically the challenges what we face in the stock market analysis is that many times it happens that the fundamental and the technical analysis often fails in predicting the stock market. So that opens a door for unconventional approaches, and among that from the unconventional approaches, the financial astrology, which deals with the movement of celestial bodies, which includes the planetary cycles, lunar phases, retrogrades, movements of the celestial body. So I have covered this part for my research work. Moving on to the astrology and machine learning, as my Astro LSTM integrates basically the astrological factors, the planet declination, as the figure demonstrate that how that particular declination is being recorded. As you can see in the figure, this is how the celestial bodies move around the Earth, and like you can see, this is an example of Moon, and this is how the declination is being calculated. And this changes as the celestial bodies are always in movement. So on daily basis, that recordings has been recorded for all of these planets. And now my Astro LSTM integrates the declination values, the planetary declination, that is the astrological factor. And secondly, I have opted the LSTM network. So that's why I have named it as Astro LSTM. The for astrology factor, planet declination for astrology, and for LSTM, the name is LSTM. Now,
my research contribution includes basically it provides a stock market prediction tools which integrates the astrology and machine learning, and it explores the non-traditional factors other than the market indicators and all to analyze the market behavior. And it is a novel perspective on the which basically focuses on and can enhances to the financial and astrological studies. Regarding the data set collection, I have, as of now, I have considered two sectors. One is the banking sector and the other is the energy sector. For banking sector, I have considered the SBI and SDFC stocks. And as far the digitized data was concerned, I have collected all the data. So I have taken the data from the year 1996 to 2023 for depending upon the availability of these data. So for banking sector, I have taken SBI and SDFC. And for energy sector, I have taken Coal India and ONGC stock. And from the stock price data, I have considered the dates and the closing price for each of the stock on the daily basis. And regarding the planetary declination data, I have recorded the data for Sun, Moon, Mercury, Venus, Mars, Jupiter, Saturn, and have executed the code for each of them individually and recorded the results. This is my proposed methodology, in which basically I have collected all the historical data of the stock price along with the data of the planet declination, and then pre-process that data, means removing all the unwanted data from that. Means I have considered only the live working date on which the share market was live, excluded all the holidays, even the null values and whatever the case may be. And then splitting the data into training set and testing set in the ratio 80-20. Then I have trained the data using the LSTM model, and then I have tested the same model, the trained model with my testing data and got the results. Talking about the results, this is the result for the first stock. So for this results, I have executed for each of the stock for the 7 planets, and for that also I have considered 3 loss functions: the MAE, MAPE, and MSC. For each of them, separate codes were executed, as you can see, and the corresponding graphs were plotted. And in this table basically shows that for the banking sector, the Mercury, Venus, and Jupiter are the governing planets as per the astrology, and this is what my Astro LSTM has reduced. So we can see for this parameter, the parameter is the lower value of the loss function and the highest accuracy. So as we can see that for this SBI stock, for the MAE loss function, I am getting the lowest MAE value for the Mercury as compared to the other, and the highest accuracy for that particular model. Similarly, for the second level, we can see that the second highest is 5 for the Venus, and similarly the accuracy is also is the second highest. So this way we can conclude that as compared to the other planets, Mercury and Venus influences the most for the SPI stock if we are considering the code for the MAE loss function. Similarly, in a similar fashion, I have for the MAPE loss function, I have tested the code and got the observation. So I am again here getting the lower loss value and highest accuracy for Mercury, and which is in principle with my astrology. As per astrology, the banking sector is being covered by Mercury, Venus, and Jupiter. So I'm getting the same results, and the corresponding graphs are also there. Similarly, for the third function, the MSC, I have considered this. So as I can see, we are getting the lower values and higher accuracy for Mercury and Venus. So overall, we can say that Astro LSTM has detected that for the SBI stock under banking sector, we are getting Mercury and Venus. And our astrology suggests Mercury, Venus, and Jupiter may influence the banking sector as compared to the others. So which I am getting the same result. Moving on to my next result, that is the SDFC stock. In the SDFC stock, I have adopted the same approach. And now here I am getting some inconsistent result. It may be the result may be inconsistent due to some ephemeris calculations, because if we talk about the ephemeris, there are several methods to compute the ephemeris which I am getting online. So that might be one of the reason, or there might be several other biasing of database or something. So that I will be exploring in my future work. But still, despite of this Sun being the inconsistent result here, I am getting some fruitful result here also for each of the loss function. As you can see, for MAE, I am getting the Venus as this. Venus as the second lowest and the second highest accuracy. Then if we talk about the MAPE, I am getting the Mercury. Mercury is the lowest value of the loss function and the highest accuracy. And similarly, for the MSC loss function, I am getting Jupiter and Venus. So this again, if we talk about this, this is the Sun is the inconsistent result here for this banking sector. As in the last case for SBI, there was no inconsistent result. Only this inconsistent result is only there for one function. Moving to the other, now this is my energy sector. I am covered the energy sector. I am considered the Coal India stock. So similarly, I have executed this as well, and we can see that I am getting the highest accuracy for the Saturn, as the governing planets as per astrology for Saturn for the energy sector will be Sun, Saturn, and Mars. So I am getting this Saturn for this. Similarly, there I am getting some inconsistent result here as well. This is only for Mercury, that it is giving the lowest MAE loss function value. Now again, I am getting the result aligned with my astrology principles. Similarly, for the second loss function, I am getting this Saturn, which governs the MAP loss function for covering the energy sector. And similarly, for the MSC, I am getting these functions which are properly aligned with the principles aligned as per the astrology. Moving ahead, I am getting one inconsistent result here as well. That is for Venus, but that is only in the one function. Now, moving ahead to my last talk, that is ONGC. Here I am getting the consistent result for all these. As you can see, initially the lowest loss value
Sorry
is
for
for.
interruption, sir. Can you just wind up soon?
Yes. It will hardly take 2 to 3 minutes.
Yes, sir, sure, sir.
Okay. So similarly, I have just demonstrated these results as well. So I'm getting the results totally in accordance. Like you can see for the governing planet as per astrology, Sun, Saturn, and Mars. So I'm getting this in that sequence as well. Then Sun, Saturn, and Mars are having the lowest value and the highest accuracy. Similarly, for MAP loss functions, I am getting the total my results as per the astrology. You can see the first level, first, second, and third. And similarly, for this MSC loss functions, I'm getting the same result here. Means here overall my functions are totally in line with as per the astrology. Now this is the basically combined result of the banking sector. If we talk about, I have just clubbed it here, and I am just showing that as per astrology, the banking sector must be Mercury, Venus, and Jupiter. And for SBI, I am getting it correct. And only for HDFC, I am getting the inconsistent result for Sun. Similarly, for the energy sector, if we talk about, so I am getting the only inconsistent result only for in case of Coal India, that is for energy sector, and for ONGC, I am getting the result totally in line with what is given as per astrology. Talking about the conclusion, so basically this is just an introduction for the Astro LSTM model, a novel model, and here I have adopted an interdisciplinary approach covering artificial intelligence and astrology. And for findings suggest that there is significantly it influences the stock market, and it opens the door for astrofinancial analytics. My future work basically have many options, like integration of additional astrology factors like retrogrades, dasha system, conjunctions, refinement of machine learning algorithm, validations upon different financial sectors that I have only considered 2 sectors here. And again, it is an expansion of astro-financial analysis. And talking about the biasing of my dataset limitations, so it may be that the stock market depends on many factors. May depends on many factors like some economic policies, some government policies, and any geopolitical events like COVID and all. Talking about the other variations, it may be due to ephemeris calculations. There are several ephemeris available like Ganesh Appa and Rishikesh, Panchang. They all have basic differences.
Sorry,
So
sir.
this was all.
There is time constraint. Okay, thank you. So how about that certificate? Excuse me, sir. The certificate will be provided you after 1 week, and the copyright PDF will be asked later. Are you fine with that?
Okay.
Yeah. Certificate 1 week, or then copyrights one PDF.
Shall I stop sharing or wait for queries?
Good afternoon, ma'am. Is it audible?
Yes. Now it's audible.
Thank you, ma'am. Good afternoon to all distinguished dignitaries, respected professors, ladies and gentlemen. At the outset, I, Arjun Kumar, and my co-host Ananya, on behalf of Department of Electronics and Communication Engineering, Amity School of Engineering and Technology, Amity University, feel honored to welcome you all on the first day of 12th International Signal Processing and Integrated Network Conference, SPIN2025. As one of the leading global universities, Amity University is dedicated to its responsibility of imparting its students a strong foundation and a platform of empirical inquisition. With this agenda, SPIN 2025 intends to bring together professionals, academicians, industry experts, researchers, and enthusiasts to discuss various emerging trends and innovations, share research results, and new directions in the field of next generation technologies. It is our great privilege and honor to have amongst us Dr. Angela Ampham. Thank you, ma'am, for joining us.
My pleasure.
Now, my colleagues will continuing with that.
Professor Dr. Angela Amferman received her PhD in optical communications from the University of Oxford, UK. She then won the prestigious Fulbright Award to work on optical devices and networks at the Research Laboratory of Electronics and MIT Media Lab, Massachusetts Institute of Technology, USA. She currently leads the Photonics Laboratory at Sunway University. Before joining Sunway University, she was Deputy Vice Chancellor of University Malaysia and Dean of Academic Affairs of University of Computer Science and Engineering. Prior to that, she was Director of the Optical Technology Research Laboratory at University Utara, Malaysia. She has also lectured at Multimedia University and served as Computing Officer at the University of Oxford, UK. She is currently on the National 5G Task Force for Development of 5G Infrastructure. She also serves on the IEEE Joint Censored and Nanotechnology Council. In addition, she is on the editorial board of the APL Photonics Journal under the American Institute of Physics and several other international journals. In addition, she has served as co-chair, Technical Program Committee, and International Scientific Committee for numerous international conferences. She has given keynote addresses at several Fulbright and IEEE events. She has won the International Academic Award by the Prime Minister of Malaysia, several Excellent Service Awards, Teaching Awards, Best Paper Awards, and Exhibition Medals. She is also recipient of the Distinguished Telecom Malaysia Scholarship. Her research has been funded by the Fulbright Foundation, Telecom Malaysia, and Ministry of Higher Education. Welcome once again, ma'am. We are honored to have you grace SPIN 2025.
Thank you.
Now, I would request Dr. Angela Anferman to kindly address the gathering with her words of wisdom. Please, ma'am.
Yeah, welcome, Professor Angela. Nice to see
Thank
you.
you. Thank you. Nice to see you again.
Yeah, thank you. Yeah, please go ahead.
Can I
Welcome,
share my
ma'am.
screen?
Welcome.
Thank you. Hi. How are you? Nice to
Last time
see you.
also we were there in the same
Yes,
session.
yes, yes,
Yeah.
Professor. Yes. Nice to
Hope
see you
you're
again.
fine.
Yes, I'm good. I'm good. How are you?
I'm too good.
That's good. That's good.
Nice to see you again.
Nice to see you. Yes. How do I share my screen, by the way? Oh, yeah, I found it.
Okay, ma'am, you may proceed with the talk.
Okay. All right. Okay. All right. The title of my talk today is on spatial modes for additional degrees of freedoms for our upcoming 6G communications network. Okay. So I'm currently leading the Smart Photonics Laboratory in Sunway University. So we're right in the heart of Sunway University. So very accessible to a lot of amenities such as medical, healthcare. We have some sort of like a retirement home as well nearby. And we have a shopping mall, one of the largest shopping malls in Malaysia. And we're also right next to a theme park as well. So we have a lot of fun games, swimming, and all other types of sports nearby as well. So this is Sunway City. It's a very vibrant city. So we have all the amenities of a modern city. And we are about 45 minutes from KL. Okay, so we're working closely with many universities around the world. We have connections with MIT, George Washington University, University of Massachusetts, Boston University, Harvard, Stanford, and of course now we have MIT as well. So today I will talk about optical communications, the current landscape. We'll also go into future extension of space division multiplexing, and what are the principles and complexities involved, and there's opportunities for 6G in MDM techniques as well as its applications for 6G. Okay, so we have here the advent of networks, Internet of Things has called for more bandwidth and more user connections to the greater network. So that is made possible by edge networking, and we can do that through many multiple accesses as well as multiplexing schemes. So with that, a lot of industries require multiplexing and multiple access, and we're working with a lot of these industries such as agriculture, we're working with the medical, healthcare, energy, and as well as immersive technology such as VR and AR. So what we're doing is we're connecting multiple user devices onto the larger network through our multiple access schemes. So what that allows is it allows us to have more connected devices, not limited to smartphone and tablets, but also sensory devices, such as temperature devices, healthcare, wearables, for example. So all of that is now crucial in developing Internet of Things in order for us to have data that will allow us to make intelligent decisions based on insights that we gather from the environment. So with that comes, of course, inevitably that comes with an increase in network traffic. So that requires multiple access as well as multiplexing schemes. So prior to mode division multiplexing, we have time division multiplexing, wavelength division multiplexing, which allows more users to access the network. All right. But due to the proliferation of Internet of Things devices, sensory devices, wearables, and other sensors that are abundant, so this is insufficient for sensing the environment. So what we need is new multiplexing schemes in order for us to be able to allow more connected devices without losing the bandwidth of the system. So space division multiplexing or mode division multiplexing allows that to happen by allowing more number of channels through the same medium. So the medium is shared now with multiple data streams through modes, through what we call spatial modes. And spatial modes are solutions of the Maxwell's equations. And the beauty of spatial modes is that they are orthogonal. So when they are orthogonal, there's no interference between one channel and another channel. So we can utilize these orthogonal channels to transmit data seamlessly without collision or without any kind of obstruction between the different users. Right. So what the benefit of this is that it allows physical infrastructure. So really what's happening now is a lot of the data centers, they're working on virtual connections. So virtual connections, at the end of the day, it will become saturated because there's no physical infrastructure to support the virtual connections. So traditionally, we use wavelength division multiplexing in order to have more and more connections. But what we now have is the space division multiplexing connection. So space division multiplexing connections allows us to have more user connections through spatial modes. And spatial modes, the beauty of that is it's orthogonal. So it can be used in conjunction with other multiple access schemes. It can also be used in conjunction with wavelength division multiplexing, OFDM, PDM, and many others. And in order to do that, we need to address mode coupling issues. All right. So generally, when we transmit one mode, all right, it is expected that the one mode will disperse into other modes. So what we do is we look at interference mitigation, techniques, which occur either at the end of the receiver or at the transmitter side. So it occurs at the end of the transmission, all right, at the receiver. So that's what we call post compensation. So that's where we try to equalize the channel, okay, the power in the channel if it's not, equally distributed, all right? Or what we can do is also to have the mitigation of the interference at the beginning. So once we are able to estimate the channel state, all right, or the amount of interference that will occur, what we do is that we inject some noise into the transmitter, all right? We inject some noise at the transmission, which will eventually cancel out the noise. So if you have noise and another noise, eventually they will cancel out each other. So that will leave you with a very clear, clear data that will be received. All right. So we do that by using a variety of techniques. So that covers photonic crystal fibers, reflective mirrors, and also using some software with AI. All right. So the first approach is using programmable mirrors. All right. So these programmable mirrors allow reflection of the signals. All right, with shaping of the wavefront. All right. So when we shape the wavefront, what this allows is it allows certain signals to be suppressed, unwanted signals to be suppressed, and those that are desirable into specific users, we are going to enhance those. So by controlling the array, what that allows us to do is we are allowed to have more signal strength in desired modes and less interference from undesirable modes. So let's say you transmit mode number 1, of course you would want mode number 1 to occur at the end. So what we do is then we strengthen the signal in mode 1 while reducing the interference from other neighboring channels, let's say from mode 2, mode 3, and so on. So how do we do this? We do this through mode shaping. So we use Fourier transforms, we use binarization. All right. So all of this allows us to control the diffraction that occurs within the setup. So what we see is that we have gained enhanced modal purity in the modes that are used for transmission. All right. And those modes that are not used for transmission, they are very minimal. All right. So using this, we have enhanced the bandwidth by more than 3 times. We've also worked with MIT for fabrication of photonic crystal fibers. So by controlling the holes as well as the spacing between the holes and the geometry and also the defects between the refractive index, we're able to then generate certain modes that can be used for transmission while eliminating those modes that are interfering with the dominant modes. So these are some of the basic ones that we have created. We have more advanced setups as well. So along the way, we've seen certain patterns that are able to create certain, mode groups, for example, and we have discovered more and more mode groups along the way. Okay, ranging from Hermite Gaussian modes, Laguerre Gaussian modes, orbital angular momentum modes. Okay, so what I'm showing here are some of the basic modes that we have, right? So we have progressed quite a lot from this, and now we are working towards more advanced modes. So if there's anyone working on orbital angular momentum modes or Hermite Gaussian modes, you're most welcome to drop a line. Okay, so here we have vortex lenses. So vortex lens is part of the fabrication for orbital angular momentum modes. So what is required for generation of these modes is a helical or a spiral phase. Okay, so it's not the intensity that will generate the wavefront or is critical or signatory to orbital angular momentum modes, but it's the phase of the wavefront. So the phase will require a spiral gradation, as you can see here. All right, with the center usually with a hole, all right? And the reason for that is we notice that most of the defects or most of the impairments that occur during propagation, most of it occurs in the center of the beam rather than at the edge of the beam. So with that, we neglect using the center of the beam to avoid channel impairments. So we've generated many types of modes in conjunction with the vortex lenses. So that allows us to have less channel impairments, as you can see here. So with vortex lenses, we can see that the channel impulse responses for the channels are very abrupt, meaning that there's no spreading of the channel impulse response into unwanted modes or into neighboring modes. Usually what happens is that when you have a very wide channel response, there will tend to be some interference with other neighboring modes. So that will cause, for example, crosstalk. Okay, while you make a phone call, that will cause crosstalk. Okay, or while you're having this, let's say, video call, then you might see other types of, other types of images that occur unwantedly. So that's all noise in communication terms. Okay, so we try to eliminate that. So we have used vortex lenses in conjunction with decision feedback. So that's shown to be very, very good for elimination of unwanted modes. All right. That brings us to the topic of adaptive equalization. So adaptive equalization uses the hardware that we showed you earlier. So the hardware consisting of photonic crystal fibers that we saw that we fabricated at MIT. Also, we have adaptive mirrors. So these are used in conjunction with some algorithms. So these algorithms are mostly machine learning and also in artificial intelligence based. And what that allows us to do is that allows us to further control the limitations of what the hardware offers. So with hardware, we're able to control the mode distribution to a certain extent. So the remainder or the slight, impairments that still occur despite having hardware control. So we control that using artificial intelligence as well as machine learning approaches. So we've done a variety of algorithms. So we've used, for example, particle swarm optimization. We've used dragonfly, bees. We've also used neural networks. We've also used inferencing system, all right, in Tagachi inference system in conjunction with neural networks. So if any of you are working on, let's say, convolutional neural networks or working on, now we have, other types of neural networks as well. So you're most welcome to have a chat to see what we can collaborate on together. So how it's used is that usually what we do is that we need to look at the diffraction orders, and from the diffraction orders, we can then design the algorithm based on Zernike polynomials and other types of polynomials in order to look at the defects in different orders. All right, so we can look at very fine defects, and we can also look at the hard effects. All right, so there are different types of defects that we can look at, and that's made possible using Zernike polynomials. So now we look at the architecture. So how is this deployed within the 6G network? So we have all these multiple access schemes. So how is it deployed? So what we do is that if you can see, if you can look at this diagram here, yeah, you can see that within, let's say within this hall, for example, over here, so you have many devices. And for IoT, these devices are usually some sort of sensors. And all these sensors, okay, you could have a temperature sensor, you could have a humidity sensor, all right? And I think Prof. Ashwani, he has, yeah, we are working on one paper together on proximity sensors, all right? So all these sensors have to be connected together in order to make an informed decision on the channel and also the number of users. So in order to do that, that's where mode division multiplexing comes in. So mode division multiplexing allows us to have all these connections for all these devices, and we can design selective multiplexing based on the needs of the central site. Maybe at the central site, they would like to have, for example, analytics on, let's say, purchasing, or they would like to have analytics, for example, on billing, or the amount of production for a certain site. So that all requires selective spatial mode division multiplexing. So that all can be manipulated and fabricated based on the needs of the system. So if you're in a, let's say, a manufacturing site, there will be certain needs where certain types of sensors will be required, and how these sensors are used in conjunction with one another in order to gain insights on the environment and to make smart decisions. So that's what we do. So we work with several industries in order to make that a reality for these companies. And we are happy to engage with all of you here as well, to work on different types of architectures for different needs. All right. And the connection could be optical fiber based, or it could be radio over free space optics, okay, or it could be pure free space optics where there's no guided medium involved. It's just transmitting the data over the atmosphere, for example. And sometimes when there is limitation on the wavelength that is allowed due to the RTU spectrum, then another alternative could be using free space optics. So free space optics allows us to transmit data on optical channels. So optical channels require no licensing, so that saves a lot of cost, especially for companies which require a lot of connections. Yet the number of radio wavelengths are limited, so we can help with that as well. And sometimes we need to have a combination of both. So sometimes if your existing channels are radio based and we need to connect it over optical fiber, we can also have radio over fiber as well as radio over free space optics. So here are some of the projects that we have done for these different architectures. So here we have utilized the photonic crystal fiber, which we fabricated earlier. So we've used it in an optical fiber system, where we can see distinct modes used for transmission. We can also use it in a free space optical communications architecture, as we can see here. So what we've done here is we have an indoor architecture with several LEDs, and these LEDs all utilize different modes. Okay, so the LEDs are used not just for lighting the room, but it's also used for data transmission. So when there are several users that are connected, all can be connected simultaneously using space division multiplexing. So that offers license-free connection, which is high speed, high bandwidth. It's also secure and no cabling and no licensing fees is involved. So we have done for indoor, we've also done for outdoor transmission, and now with the advent of reflective surfaces, I'm sure you've heard of that. So now buildings are used as reflectors. Okay, you have buildings, you have lampposts, okay, you have various regular stuff, you know, while you're driving that are used as reflectors. So these reflectors help to scatter the light from from the source to the destination. So along the way, you will have amplification, and you will have redirection of the signal so that it can reach the destination securely and also at a high signal strength. So we're also working in that on that, and we have hybrid networks. So we have radio optical networks. So radio optical networks allow us to connect to existing radio networks. So in certain circumstances, the network base station, the radio base station exists, but in the event of, let's say, some disaster, let's say a fire, a flood, so what we can do is we can reroute the signal from that particular base station using optical networks. So optical transceivers are used to relay the information from one base station to another base station. So we've also done work in that as well. So there are various opportunities for radio over free space optics connection. So that usually occurs when you have, let's say, emergencies. Let's say you have medical emergencies, or there's an emergency due to natural disasters. So we've been called to help in these circumstances. So this is some of the results we obtained. So you can see that each channel will have distinct channel impulse response. So there's less scattering, or the signal strength in the unwanted modes are kept to a minimum. So that allows you to have less or minimum crosstalk to other channels. So this is what you can see here. All right, so this also applies to millimeter wave, terahertz as well. So those of you who are working in radio and you would like to, you know, extend your expertise, you're most welcome to collaborate with us as well. So I hope you enjoyed the talk. So we welcome collaboration in various aspects, in communications, in AI, towards space division multiplexing, and also multiple access in order to have an integrated networks. So at the end of the day, what we want is a connection everywhere and anytime. So that can only happen when we have good multiplexing and also multiple access that will cover a wide range of spheres from space, from optical satellites all the way up to drones, high altitude platforms, terrestrial, all the way to underwater networks. So all this is possible to make Internet of Things an integral part of our society. So we welcome collaboration in this realm, and we offer scholarships and also financial aids to bright students. So time every now and then we have offers for scholarships. So you're most welcome to join us. Okay, and you can include your current supervisor. If you're doing masters, then you can include your current supervisor with us for your PhD journey. All right. We also have an upcoming conference. So you're most invited to join us as well to submit papers, joint papers together. I've already given Prof Ashwani the details, so you can liaise with Prof Ashwani if there's any interested student or postgrad interested in this. All right. So that's all for today. So you're most welcome to check out my LinkedIn for any calls every now and then. So thank you very much, and I hope you have an enjoyable rest of the conference. Thank you, and most welcome to come to Sunway.
Yeah,
Thank you.
great.
Thank you
It's
very
really
much, ma'am.
wonderful to listen you, and you have opened many opportunities for the students. I always encourage my student to explore the opportunities, and now you have opened the door of the opportunities. So it's up to them that
Thank
how they encash it.
Thank you, thank you, thank
Very
you. We
great.
have a good connection with your university. Yes.
Yeah.
Thank you. Thank you very
Thank you,
much.
Professor
Thank
Angela,
you,
for
ma'am. We
joining
will
us.
definitely explore. Speaker off.
Thank
Yeah,
you.
so Dr. Nidhi, please go ahead as per you said.
Yes, ma'am.
Also, we are there.
Hmm. Hello, ma'am. We will definitely explore the possibilities that you have actually told, and this is an interesting talk on 6G. So I
Yes.
myself work in network, so I will definitely have some students, and we will explore some possibility.
Sure,
Here
sure.
we have projected this in the online room, so maybe
Sure.
many of the students are interested.
That's
So
wonderful.
we will
That's
provide the
wonderful.
link. Thank you
That's
very much. It is
wonderful.
very interesting talk.
Thank you, thank you, thank you.
की आवाज नहीं आ रही, स्पीकर ऑन कर।
Yeah, Professor Angela, please stay for a minute because there is a formal closing of this your talk. So yeah, go ahead.
May I invite Dr. Nidhi Gaur to present a certificate to our esteemed speaker, Dr. Angela Amphawan, as a token of gratitude.
Congratulations.
Oh, thank you
Ma'am,
very
so here we are presenting the certificate. We will be sending you through the email. And as a token of gratitude, we are presenting it in an online mode. Thank you very much
Thank
for the
you.
talk.
Thank you so much.
And
Thank
now we are proceeding with the paper presentations in the next session. If you
Yes,
are
yes.
interested, you may keep join.
Yes, thank you, thank you, thank you.
Okay, bye.
I would like to call upon Dr. Nidhi Gaur to present a sapling to Dr. P. Banerjee. Please. A brief introduction about our esteemed speaker. Dr. P. Banerjee received the master's degree in physics and the PhD degree from Burdwan University, Burdwan, India, in 1971 and 1976, respectively. He joined the National Physics Laboratory, NPL, New Delhi, India, as a scientist in 1976 and is currently the head of the Time and Frequency Section, NPL. He has been working on time-scale generation, time dissemination techniques via a geostationary satellite, GPS, and GLONASS, electronics instrumentation, development of microprocessor-based systems, etc. Dr. Banerjee is currently the Vice Chairman of Commission of the Electromagnetic Metallurgy of International Union of Radio Science, URSI. He is a Fellow of the Institute of Engineering and Technology, formerly IEE, UK. He received the Young Scientist Award from URSI in 1985 and the IETE Hari Ramaji Toshniwal Gold Medal in 2006. Welcome once again, sir. We are honored to have you grace SPIN 2025.
Thank you.
So would you like to call upon the paper presenter or would you like to me to present? Right. Yeah, so how to share you in the calendar.
Good afternoon. Welcome all the delegates and the speakers of these sessions. There are it's a hybrid session, so there will be both one presentations online and there will be some 5-6 presentations offline that are in person. So as because we are running short of time, so I request you, all the speakers, to complete your talk latest by 10 minutes. And your cooperation is very much needed for the smooth running of the session. Thank you very much. And I'll call the speaker one by one. And I request all the speakers to load the PPT presentation if required well in advance so that we do not waste time in between much. Thank you.
Now I would request paper ID 134 to present his or her paper. Before we proceed, the session, could I kindly request to see your identification proof?
Good afternoon, everyone. My name is Nalini, and today I'll be presenting my research on plant leaf disease detection using machine learning, which focuses on leveraging CNNs for automated disease detection, classification, and cost-effective mitigation to support sustainable agriculture. So without taking much of your valuable time, let's get started. Okay, so in this presentation, we'll cover the abstract, introduction, methodology, results and discussion, conclusion, and references, thus giving an overview of our research and findings. So now let's move on to the abstract section. So this study presents a machine learning driven approach using convolutional neural networks to detect and classify plant leaf diseases. The model first determines whether a leaf is healthy or diseased and then identifies the specific disease affecting it. If we talk about the innovative features, then the system introduces a disease progression analysis. So if we talk about the innovative features, then the system introduces a disease progression analysis, which predicts disease severity over time and estimates the time until leaf death if untreated. Additionally, it also provides targeted mitigation strategies to help farmers take proactive measures. And if we talk about the cost-effective management, then the approach includes a cost analysis of suggested treatments, allowing farmers to make informed decisions based on the economic feasibility of disease control. Thus, this holistic method enhances agricultural productivity by enabling early detection and strategic intervention. Moving on to the introduction part, as we all know that plant diseases threaten global food security, causing significant yield losses and financial strain on farmers. Traditional visual assessment methods are quite slow, labor-intensive, and subjective, often failing to detect diseases in their early stages when intervention is most effective. So deep learning models, especially convolutional neural networks, which is again CNN, offer a promising solution by autonomously analyzing plant leaf images, identifying the visual disease patterns, and classifying diseases with high accuracy and speed. This study presents a CNN-based model trained on a diverse data set to classify leaves as either healthy or diseased, pinpoint specific diseases, and enable rapid automated diagnosis. The research also introduces. Sure, I'll find it. Sure. Okay, so as you can see, the research introduces disease progression analysis, predicting the time to leaf death if untreated, and of course, analysis of mitigation strategies as well to support economically viable decision making for farmers. So next we have the methodology part, in which we mainly emphasize on the 4 steps, which is dataset preprocessing, in which a diverse dataset was curated, and image preprocessing techniques like resizing, normalization, and etc. are applied in order to prevent overfitting. Next is the design of the CNN model architecture, in which a deep CNN is designed with multiple layers in order to extract the hierarchical features for precise disease classification. Step number 3 is disease progression analysis, in which our module tracks disease severity over time using sequential images and image processing. Also, a severity versus time graph predicts leaf survival, thus enabling proactive intervention. And lastly, cost estimation of mitigation measures, in which the system suggests the cost based on the treatments provided, allowing the farmers to make cost-effective decisions rather than spending blindly on expensive treatments. So now let's talk about the results and discussion part. As you all can see on your screens, there are two leaf images. One is diseased and the other one is healthy. The first image shows a diseased leaf, and the disease is tomato leaf blight, with a suggested mitigation measure, including the treatment and its estimated cost. And as you can see on the screen, the second image displays a healthy leaf, confirming no action is needed while advising continued optimal growing conditions for plant health. Next is the disease progression graph for the tomato leaf blight disease, which we discussed in the previous slide. So the graph illustrates how this disease severity increases over time As you can see, it starts with a very low infection rate, but accelerates rapidly after the initial phase. Next, we talk about our model accuracy trends. So our CNN model basically achieved a high consistent accuracy of 96.05%, with training accuracy stabilizing and validation accuracy showing quite fluctuations due to dataset variability. Along with this, the model achieved various confusion matrices, right precision, recall, F1 score, and accuracy, showing high reliability in classifying plant leaf images as healthy or diseased with balanced performance. And now this is the comparison table, how our CNN model outshines various other traditional machine learning models. As you can see in the table, our CNN model definitely outperforms with an accuracy of 96.05% and disease identification. It effectively detects specific plant diseases, offers cost-effective mitigation insights, and predicts disease severity features which are lacking in previous models. Along with this, various pre-processing techniques like resizing, normalization, and augmentation enhance the model robustness, ensuring better adaptability. So all these things confirm the superiority over the various other traditional approaches in the agricultural disease detection. So in order to conclude, the CNN model accurately classified healthy and diseased leaves, effectively distinguishing between disease types for precise identification. This analysis also provided insights into disease progression, enabling various timely interventions and improving overall agricultural productivity as well. Additionally, the cost effectiveness study highlighted economic benefits, helping farmers to minimize yield losses through early detection. And as far as the future prospects are concerned, then the future work involves expanding the data sets, like integrating various environmental data and developing real-time detection systems for enhanced agricultural sustainability. And these are the references for the same. That's it from my side. Thank you.
Presentation, but
When you compare the result, you mention one name, that is RM. Are we able to understand? Can you just be and R? So SVM is, I think, support rate condition. Yes. And what is RM?
It's one of the machine learning model, basically a traditional machine learning models. Basically, I compared our CNN model with the previous traditional machine learning models. How our models? Yeah, right. It's one of the machine learning models, I can say.
yes, I would like to understand one thing from you that say convolution neural network.
Yes.
So you have a training.
Yes.
What are the parameters that you use to train, and how long will you have to train? Rather, how many numbers of
Epochs.
and second thing is that how do you get those parameters? Normally, we by physical observation we identify. In these cases, what do you do? So light on it.
Sure, sir. So basically, if we talk about the parameters, then as you can see, the CNN model architecture. Basically, we used 3 layers of the CNN model. One was the convolutional layer, which was used for feature extraction. Pooling layer was used for dimensionality reduction. And the last layer, is fully connected layer, we used for the feature classification. So for training, we run approximately around 100 to 200 epochs. And if we note the time, like how much time this code takes to run, it takes around 2 to 3 hours to run. So yes, we trained, and also we applied various pre-processing techniques in order to clean the raw data like normalization, resizing, and data augmentation. So by using these 3 techniques, we clean the data to in order to like rectify if any missing values are there.
Yeah. What are the parameters you use to train the software? Then how long you have to train it, and then you will have to predict it.
Right.
Yeah, this is the normal process in the environment, whether it's a convolution or anything.
Yes.
So you tell me very clear way that what are the parameters, how do you get those parameters? For example, you would like to see the color.
Right.
Okay. So color, how do you take those color?
So it's through CNN model only. It's through its automatic feature that it automatically extracts the features from the images. Like there is no manual intervention.
Of the color. Suppose you have a disease leaf.
Yes, sir.
Okay. And you will have to extract some parameters from that, that whether it is at all diseased or not. Okay. So one is physical.
Right.
If you see by eyes, how do you feed the parameters to the software?
Right, sir. Exactly that part was done by my co-author. That's why.
The eye will see.
Right, right,
But
right.
what parameter you will get there.
Right, sir. Got it,
That
sir.
must be clear.
Agreed,
Otherwise,
sir.
how will you apply it?
Right, sir.
I want to know that.
Sure. So I'll definitely look into it. More details. Thank you, sir.
Now I would request paper ID 270 to present his paper. Am I audible? Now I would request paper ID 345 to present his or her paper. Before we proceed with this session, could I kindly request to see your identification proof?
Am I visible?
Yeah. I kindly request that presentations to be kept within the duration of 10 minutes each. Thank you. You may start.
I cannot share my screen right now.
You can share your screen.
Okay.
Your screen.
Ma'am, is this audible? Ma'am, is this audible?
Yes. Am I audible?
Yes, ma'am, you are audible.
Okay. Good afternoon, everyone, respected panel, esteemed guests, and my fellow researchers. My name is Hiba Afzal, and I am honored to present our research on the development of an IoT-based autonomous human tracking trolley. This research was conducted at Amity University, Noida, and focuses on the automation of material handling using advanced sensor technologies. Our paper ID is 345. This presentation includes the introduction of our research, the research objectives, system architecture, system implementation, methodology that we have adopted, the results and observations, the conclusion, and the references. Now, the problem statement. The increasing demand of automation has significantly influenced sectors such as logistics, healthcare, and transportation. Manual material handling processes are often insignificant, inefficient, labor-intensive, and prone to human error. As industries shift towards intelligent automation, there is a growing need for autonomous systems that can seamlessly interact with their environment and improve operational efficiency. The limitations of existing system, high cost and maintenance. Vision-based tracking systems require expensive hardware and extensive computational resources for image processing, making them financially impractical for large-scale implementation. They are insignificant in low light and crowded environments. Tracking accuracy significantly drops in low light conditions or crowded environments, as multiple moving entities can disrupt the recognition algorithms. Now, the third point is inaccurate due to obstacles or obstructions. Physical obstacles such as furnitures, walls, or equipment can interfere with the line of sight tracking mechanism, reducing reliability in dynamic settings such as warehouse or hospitals or marketplaces. Now, the objective. To address these challenges, we propose an IoT-driven autonomous human tracking trolley that leverages Wi-Fi RSSI mapping, ultrasonic sensors, and IR sensors that are infrared light sensors. This system ensures cost-effective, robust, and precise tracking without dependence on vision-based technologies. The research objective.
Wi-Fi RSSI-based tracking. Our system relies on the received signal strength indicator, that is RSSI value of Wi-Fi signal from a designated operator's device to maintain an optimal following distance. Second, ultrasonic and IR sensors. Ultrasonic sensors detect obstacle in real life, while IR sensors enable turn detection, ensuring smooth navigation in complex spaces. Load management. We have included a load cell that continuously monitors and measures the weight of the cargo being carried. If the weight exceeds the predefined threshold, an alert buzzer is activated to prevent overloading. The fourth research objective is Bluetooth remote control. This system also features a Bluetooth-enabled manual control mode, allowing an operator to take control when necessary, particularly in confined or high-traffic areas where RSSI values are not that good to rely on. The system architecture. The hardware and software components were carefully selected to optimize tracking accuracy, response time, and the system efficiency. The components used are shown on the figure. ESP32 microcontroller serves as the central processing unit responsible for real-time decision-making and Wi-Fi communication and data processing. Ultrasonic sensors provide obstacle detection, while IR sensors enable turn detection and adaptive movement. A load cell is included, which is used to monitor cargo weight, ensuring compliance with safe load limits. A Bluetooth module allows for manual control, offering flexibility in operational scenarios. Now, system implementation. ESP32 as central controller. The ESP32 controller with the Wi-Fi and Bluetooth capabilities manages real-time tracking, control, and data processing using the Arduino IDE. That is the platform to use to code for ESP32. System sensor integration for tracking and navigation. Ultrasonic sensors detect obstacles. IR sensors assist to turn detection, and Wi-Fi RSSI values enable accurate human tracking. Operation identification and safe following distance. A smartphone application provides unique identification that ensures that only one person is connected with the trolley at one time, ensuring the trolley follows only the designated person while maintaining 1 to 5 meter distance. Load monitoring and safety protocols. A load cell interfaced via an ADC continuously tracks trolley weight, triggering safety measures if load exceeds the threshold. Manual control and data logging. A separate Bluetooth module allows manual control when needed, while the ESP32 lock keys operational data for performance evaluation. Now, the methodology that we have opted for this.
Due to time constraint, can you wind up?
Yeah, sure.
Thank you.
The research and observations that we have concluded in this research. The RSSI values were analyzed with and without obstacle. That is shown on the bar graph on the side. The system, the tracking distance, that is the optimal tracking distance, is 5 to 5 meters. That gives the excellent results. Now, the obstacle detection, we have successfully implement the collision prevention with the ultrasonic and IR sensors, the weight limits that I have told you already. Now, the conclusion. We have enhanced logistic automation. That is the need of the research. Also, advanced tracking mechanism, adaptive following and safety, the obstacle avoidance and collision, load monitoring system, and the scalability and future ready. That is this device can be used in airports, also in shopping areas and in hospitals also. So these are the references that we have looked into for our research. Thank you.
there any question? No question? Because I was a small inquiry, how did you navigate the position? Other, how do you detect the position of the your trolley?
Sir, we have made an app that is the unique identification for between the trolley and the person who is using it. So when the trolley is activated and the app is connected, we have connected it through the Wi-Fi, and the Wi-Fi RSSI values will tell the person's position to the communication of the trolley, and through the sensors we will navigate the person.
Determine the distance of its movement.
Sorry?
You determine the movement of the trolley by tracking its distance, how much it has traveled.
Sorry, your voice was not audible.
What I'm trying to say is to know the position. You will have to know from initial position how much trolley has traveled, and so you can track the next position by that maybe object is there. Otherwise, navigation has some meaning. We talked about tracking and navigation. Maybe okay. Maybe you are not able to understand what I'm trying to say. I talked to there.
Yeah, actually, I'm not getting the question you're asking.
Okay, well, I'll discuss later. So we do not have time much. Okay, thank you. Thank you, Viva, for the
Thank you.
presentation.
So next.
Hello. Yeah, hi, Professor Harry.
Hello. Hello. Can you hear me?
Yeah, yes, we can
Oh,
hear you.
good. I'm
How
just,
are you?
very well, thank you. And yourself? Let me
Yeah,
just get my video going. There it is.
yeah, good, good,
Okay.
good. Yeah, so our director, Professor Manoj Kumar Pandey sir, has also joined.
Hi, Professor
Oh,
Hari.
hello. Lovely
How
to
are
hear from
you?
you. Very well, thank you. So all's going well with the conference?
Yes, everything is fine.
Good.
Yeah,
I'm
so
delighted
this
in.
morning during the inaugural session, Dr. John Jenkins has joined from NASA.
From NASA, right.
Yeah, yeah.
Oh,
And
yeah, no, he's,
Dr. Vivek Lal also joined in the inaugural session. Yeah,
yes. Oh,
yeah.
that's fantastic.
We were missing you because it was a midnight for you.
Yeah, I tried to reverse it this time. So this is like very early in the morning. So
Yeah. So very good morning to you.
thank you. Well, good evening to you. So-
Thank you. Your session
Good.
will be started in next 2-3 minutes. So,
Oh, perfect.
so
Perfect.
it's a pause time for all of us.
Yeah.
Yeah.
Oh, I look forward to that. That's
Okay, all the
fantastic.
best, Dr. Hari.
Thank you very much.
So, are you planning to visit India?
Yes, I'd love to. That would be really nice. I'll definitely come by and see
And
you guys if I could.
this time there was a great occasion of Mahakumbh. You could have
No,
taken advantage. Mahakumbh, a kind of festival, 1 month festival in India
oh,
is going on.
really? Oh, really? What's that? What's that about?
Yeah, it's about to have some holy bath in Prayagraj, India, right?
Got you. Got
Yeah.
you.
So many people, maybe around 60 crores have already taken bath there at the river.
Oh, wow. Wow.
And
Next
even though
time.
some big personalities have also visited India and they took
Yes.
bath there.
Oh, that sounds amazing. So,
Yeah.
that's every year? That happens every year this time?
Yeah, it is there and it will happen till 26th February.
Oh, okay.
It
Okay,
has
so that's
started on 13th of January.
so it's about a month roughly, right? Well, over a month and a half.
Yes.
Yeah. Oh,
So
wow.
if you search, you will find about the Mahakumbh.
I'm going to write it down. How'd you spell
Yeah,
that?
Mahakumbh.
Yes. Yes.
Mahakumbh.
Got it. I'm gonna look next time.
Yeah, it's quite interesting one. And it comes after 12 years.
Oh, really? Oh,
Yes,
so
yes.
it's really rare.
And now this time, what's
Yes.
about the star situations is came after 144 years. So it is even the great occasion at this time.
Yes.
Yeah.
Wow. Wow. So, which calendar? How does it work? I mean, how do they decide on when it is? Is it
Yeah, they follow
a
the
lunar
Hindu.
calendar? The
Yeah,
Hindi
they
calendar?
follow the Hindu calendar. Yeah.
Yes.
Mhm.
And that's based on it's based on like the moon or the sun or what's the how does
Moon.
the moon? It's
Yeah,
a lunar
yeah.
calendar. Yeah. Okay. That's fantastic. What a shame I'm not there. That would have been amazing. God.
Yes,
Really
yes.
rare. Yeah. Well, next time. You're holding this conference now every year, the spin?
Yes. It is every year. Yeah.
Yeah. Okay. So hopefully next spin. Next spin
Yes,
cycle.
definitely. We will be waiting yours. And we will plan some visit to some of the holy places like Ayodhya. There is Ayodhya or
Yes.
Prayagraj or even Varanasi. We will plan something.
Oh wow. That'd be
Mm.
lovely to see. So
Yeah.
definitely next time.
Yeah. Okay, now, so I would like
Yeah.
to call upon Dr. Nidhi and she may start the session formally. Dr.
Wonderful.
Nidhi, are you there?
Hello.
Yeah, I think echo is there. Yeah, Dr. Nidhi.
Hello, sir.
Yeah, please go
Hello.
ahead as per your schedule.
Welcome to the Amity University. Dubey sir, our previous session is still in progress.
How much time it would take?
2 paper presentations are scheduled.
Okay, okay. So,
what
because
you will-
it would be a very good morning for Professor Harry, can
Oh.
we pause those 2 papers and after the session can we continue? If authors are agree,
Uh,
if presenters are agree? Eh?
Can we shift to the session, means the presenters?
It's a 30-minute talk after that.
Okay, sir.
They are agree?
Can you please ask the authors? The keynote certificate we will provide. नहीं जिनका previous presentation उनका certificate दे देंगे.
Have they given consent?
Arjun, have the authors given consent? Shall we start the talk? Yes, ma'am. Okay, we can start the talk, sir.
Oh, that's wonderful. That's wonderful.
Okay,
Great.
okay.
Yeah, Professor
Thank
Harry,
you.
so your talk and thereafter 2 more research paper presentation would carry on, right? So Dr. Nidhi will carry on thereafter. Yeah, please go ahead.
Yes, sir. So I welcome you on behalf of Amity University, and I look forward to your presentation and further collaboration. Thank you, sir.
Thank you. Thank you. Should I begin?
Yes, sir. You may please begin the presentation.
Beautiful. Thank you so much. So, good afternoon, everybody, and thanks so much for joining for my presentation, my keynote presentation. Before I begin, I just wanted to thank Amity University and also the SPIN conference for this kind invitation and the honor, actually, of presenting at this conference, which is an amazing conference with so many great presenters and so forth. And as I said, I'm really honored to be a part of this. So today, in my presentation, first of all, my name is Professor Harry Ruder from the University of Toronto. And in my presentation today, I want to talk a little bit about new opportunities in optoelectronics with nanostructures, in particular 3.5 nanostructures. And my presentation will have 4 parts. The first will be a very brief introduction to try and set the stage for the next 2 parts, which will be discussing the engineering of highly efficient heterostructures, quantum dot heterostructures, for absorption in the first section and for emission in the second. So the background in that first section will talk about the critical things that need to be addressed in order to make efficient devices for those 2 applications. And in the first application, I'll talk about saturated absorbers and mid-wave infrared detectors. On the second, I'll talk about emitters such as lasers and also emitters for quantum information processing. And after that, there'll be a brief summary and conclusions. So, sorry, it's not moving. Slide, it's not moving there for some reason. There we go. Okay, so in this slide, I just want to draw your attention to, let me just put this thing over here. Sorry. To the importance of understanding the energy spectrum of states in nanostructures. In fact, the reason why we talk about nanostructures in the first place, and that is that when the potential distribution in these structures is such that carriers are confined to this, and so if you look at this example of this quantum world, the one on the left here, let me just put a laser pointer on. Sorry. Yep. When we look at this schematic on the left of a quantum well, you can see that there's hard wall potential from, in this case, the dielectric, which is air, to the semiconductor, which confines electrons within the de Broglie wavelength. And so we have standing wave states in this dimension here, whereas in the other two dimensions, we would have traveling wave or free wave states. In the confined dimension, then, we would have a series of energy levels whose separation will depend on the thinness of this sheet. So the thinner the sheet, the further apart the separation between these levels are. That's illustrated here in K-space, this diagram where the traveling wave states are given at each of those allowed energy levels. This would be the first one, and this would be the second one. And on this diagram, which shows the number of available states per unit energy range, we again have the ground state, E1, let's call it, this first excited state, E2, and the third state. And we build up in increments, as you can see, states as we move from E1 to E2 to E3. What you should notice is that if we didn't have this structure, but we had this dimension essentially as large as the other dimensions, then we would have a three-dimensional entity. And as long as we conserve the atoms, the density states would look like this continuous root E dependence. The number of states in here is going to be the same number of states here because it's the atoms bringing states. So what's actually happened, and if we look down to the case where we have three-dimensional confinement here, where they're all traveling wave states, and therefore we have three quantum numbers for each degree of freedom, for example, L, M, and M for this delta function here, there will be a series of these spikes which will contain exactly the same number of states as we had in the original or in the two-dimensional case. So quantization of these nanostructures, in this case, have taken the states and concentrated them. The more we have dimensional freedom reduction in terms of free movement. So the fact that we can change the dimensions, we can change the energy spacing, and we can reorganize state space means that we have great ability to design these optoelectronic devices. How do we actually achieve that? We achieve that in our case by, for example, using molecular beam epitaxy, MBE, to realize this unprecedented control over spatial dimensions and materials indeed, because the potential landscape can be dictated by the different materials, the cladding material, let's say, and the core material in those structures. Cladding being the air that I referred to, which could be a different dielectric, and the core being the semiconductor, which was shown. So we can, if we can organize such that, for example, we have dots, this is the lower one, which are all the same size, then we would have the emission spectra would be for dots with the energy level spacings all the same, and every one of these would contribute a state to that system. We could do it with a wire system, nanowire, if we used a catalyst which determines the wire growth, and the catalyst had the same size everywhere, such that the vapor, liquid, solid grown wires were all the same. And so that's kind of a basic principle. I'm going to talk about trying to enhance and maximize the response of these systems. So let me start with the first topic, which I said was to harness absorption in specially designed nanostructures. So if we have a nanostructure designed with potential landscape, and let's just focus on the conduction band for a minute, the size will determine the energy spectrum or the spacing of these states and number of these states up here. It will also determine the valence band. So there's two types of absorption transition, which are transitions from these occupied states to these empty states here. We can either go between the valence band states and the conduction band states, or we could go between the allowed, for example, conduction band states here. We call the first one interband, and I'll discuss that application now. And in the next subsection, I'll talk about intraband, between the bands over here. In both cases, the general principle of how strong absorption is will depend on the number density of occupation of the initial state and the number density of non-occupation, or how empty are the final states, because you can only have a transition from a filled state to something which is open to take that carrier, the electron. Secondly, energy conservation dictates that the separation between those states must be the photon that we're trying to absorb, and the number of transitions will depend on the joint density of states, which is JDOS here in this diagram, which is how many states are available here and how many states are available here. So the first example I want to give on that interband absorption is the saturable absorber mirror using quantum dots. And the basic idea is that you can have a stack. You can have a stack, which is shown in red, of quantum dots. And behind it, we have a mirror, which is, in the case here, a Bragg mirror. So if light is incident, high power laser light is incident on the stack, if there's absorption here, it will, while there's absorption occurring, it will take carriers from the stream, this light from the stream, and block the light from penetrating and coming back through the system for that period until absorption stops. So let me go through the logic, and that's basically the switching idea, which is based on this round trip where light can move through the system, dictated by the absorption of this layer. So let's talk about how it works. So the high power incident light is absorbed in the quantum dot layer. And the quantum dots are sitting essentially in the mid gap here. And how does it get absorbed? Well, light is excited from ground states over here up to the excited states, relax quickly into the quantum dots. And while there's absorption in the quantum dots, they're blocking the flow of light. So basically we have the states emptied beneath and filled above while this is going on. So we call it a population inversion because a normal population would be filled lower states and empty upper states. So in that period, we have a transparent system, as I kind of mentioned earlier. And the Bragg waveguide, the Bragg stack here, it reflects the light back through that cycle to the quantum dot layer. And during the round trip, the idea is that the fast relaxation through the quantum dots, through those mid-gap traps, is basically controlling this process. And once those states empty, we can again start the process. And so we have the possibility of picosecond, because that's the time, relaxation time that occurs for these mid-gap states. We have picosecond mode locking because we have this cycle, which is determined by the length and the time of these dots. So we can engineer this thing very nicely. Indeed, what we did was we produced layers upon layers of these quantum dots, because as I said to you earlier, the idea is the more effectively oscillators in that matrix element, the more absorption we get. And the Bragg mirror also has to be an extremely deep stack to get good reflectivity and control also the round trip lifetime. And the whole system was performed by basically having the pump laser, a dichroic to back reflect the light when it comes back from the sample, which is the blue thing here, and is shown in the detail from the TEM over here. And so the pulses that we got out of this thing were 24 picosecond, some of the shortest mode locking people had observed that time, with a rep rate around the 65 megahertz. And you can see that that's in fact the mechanism, because if we look at the cavity absorption, you'd have the Bragg stack, because it's so many mirrors effectively, so many reflectors in this thing, and it's flattening out which should flatten out to a top hat. The dip here is the dip due to the absorption of these quantum dot layers, which happens right within the band pass here. So that's a very nice kind of demonstration of the fact that we can engineer through interband absorption, we can engineer a very fast and efficient mode locking system. Let me do the next example I want to talk about is a similar idea, but now for intraband absorption. And in this case, I want to focus in on the role of infrared absorption for infrared detection. So let me just go back to basics again. So the absorption rate is going to depend on the matrix elements coupling those interband states. And there's going to be a broadening, and we'll talk about the broadening in a second, as well as the occupation factors we spoke about. And of course, there's non-equilibrium here. So we're talking about the quasi-Fermi energy separations controlling the occupation of the ground subband state and the next excited state or the excited state. And if you look at traditional quantum dots, which are strands crescent plots, you see weak absorption and broad absorption. And the reason for that is because the areal density of quantum dots, which are these absorbers with those interstates we're looking at, is very low. So you don't have sufficient number to get a decent absorption. Secondly, in homogeneous sizes, that not all the dots are the same size. And right back to the first slide where I introduced the topic, if the thickness of that sheet was different, the energy level spacing, for example, if the sheet was wide, the spacing would be close of energy levels, and if it's narrow, they're far apart. So with an inhomogeneous size distribution, you smear the transitions over those various size allowed transition energies. And that both lowers the absorption rate, because we have less dots, and also smears open or broadens the response. How can we make an efficient infrared detector? Well, the answer, and these limitations are written over here: the broad emission, the large distribution, low areal density, and so forth on the left. The answer is can we make all the dots the same and make many of them? And that's where we did some work on block copolymer lithography, where the block copolymer allowed us to make extremely small, sub 20 nanometer even size, 10 nanometer size, every dot the same. So we have large densities of tiny dots, which means the separations are all the same and well defined. So uniform size and spacing, relatively small, which means strong confinement, and very high areal densities. And here's the result. So I'll just, what we did was we made the quantum dot system into a pin structure, PIN structure. So there's gain in this, just like there would be in a pin in a single photon detector if you have that, like a Geiger mode type of photodetector. And it gave huge response in the infrared. And if you just, and obviously we can tune it by tuning the size through the templating. And here's an example of thermography of looking at one of my students' heads. And what that's basically showing you is the noise equivalent power is amazing, that we can do factor it down virtually at the single photon level type of detection with these high arrays. So that's an example of using the organization and patterning of these dot systems to make extremely efficient infrared detection. Now, the other side of the coin, which is the next topic I want to talk about, is emission. So with emission, the diagram remains the same, except now we're looking to take an excited state population, which is hopefully occupied, to an empty state population, which is unoccupied, so that that transition can occur, an energy conserving transition where the difference E2 minus E1 is taken up with the emission of light. And again, the same joint density of states argument applies for the joint density states between E2 and E1. If this was in 3D, because of the dispersion and because of the density of states distribution, you would end up with a broad emission. With the exception of putting this in a cavity, we get a broad emission spectrum. So again, we want to exploit the idea of ordered nanostructures. And in this case, we took advantage of the work of Matsuda and Fukuda a long time ago, who showed that you could make ordered arrays, hexagonal arrays of pores in aluminium. And so these are actually aluminium oxide when you oxidize them in various electrolytes, so sulfuric acid, nitroxylic acid, and phosphoric acid. And by picking the electrolyte and anodization conditions, so for example, let's say oxalic acid, you can run along this curve and get pore diameters, as you can see, from 20 to 90 nanometers. Or with sulfuric acid, you can make pores below 20 nanometers. So one can make extremely fine structures, and these pores are through pores. So when you break and you remove the base and van der Waals bond it to a substrate like this, you can see through pores. So we can get dense arrays of pores, which means many oscillators for light emission and with size control. And moreover, these can be coupled, these systems. So here's some examples of thin and thicker templates which we used to prepare, and I'll show you how, the quantum dots. So the principle of the preparation is as follows. We used molecular beam epitaxy to individually prepare layers, and the layers we prepared in this particular example would be, say, gallium arsenide and either aluminium gallium arsenide or indium gallium arsenide layers. And we can alternate by shuttering off the fluxes of these elements by putting a shutter across here, and the growth rate being very slow. They're typically about 1/10 of a monolayer per second. We can prepare very, very high quality layers, one after the other in these pores. And the way this works is that you can grow almost any material in this type of approach because strain is relieved by the fact that you have a critical size argument here that enables the dots that are in these pores to change their shape to adjust and compensate for mismatched strain. So in principle, you can grow single crystals of virtually anything in heterostructured form, in heterostructured quantum dot form, as shown here. So you can either grow homogeneous arrays like these gallium arsenide arrays as an example, or this is an example of growing outgas-gas layer by layer structure in dot form, as shown by this schematic, where we have aluminium gallium arsenide barriers and gallium arsenide wells, except this dimension here is less than the de Broglie wavelength. So three-dimensionally confined disks separated by barriers so that they can actually be double well type of states. Right? So you can have bimolecular states, etc., in each dot, and each dot can be coupled. So you can build complicated, dense nanostructures using this approach. So in order to test their response, we did photoluminescence measurements. And how did we do that? We did that by using a titanium sapphire laser, a Mirror 900, which can run in femtosecond or picosecond mode. It's pumped by a Verdi 532 laser, green laser. And then with this broad spectral tunable laser, we can either double it or we can leave it as is, and then look at samples which are in the cryostat, which means between pumped helium 1.6 all the way to room temperature if we like. And we can look at both the spectral and the temporal. The Hammer-Mezger street camera gives us temporal, and the monochromator or spectrograph in this case gives us the spectral information as a function of time. So we can look at relaxation. So for example, just those the quantum dots I spoke about in the satchel absorber, we can actually see the lifetime of carriers in those dots transitioning in a system like this. So the statement I made earlier about spectral broadening because of size effects, we can test that too. So in our system, we built a confocal micro PL system, so we can actually use a pinhole to effectively sample where we look. And we can look at individual dots in an array, or we can broaden it without the confocal system to look at the array. So we can see the inhomogeneous broadening and also the response of single dots. So the system looks something like this. It's on a bench. You've got the Thai sapphire sitting at the back here. You've got an OPO. The pump is sitting behind here. The camera and all this part here is part of the confocal imaging system. Here's the helium cryostat, street camera, the spectrograph, and so forth are on this bench. And you can see the light paths here coming in and out through the essentially the microscope. We can look at dots individually, but with less efficiency through cathodoluminescence, that is using a scanning electron microscope, low temperatures. But I'm going to show you results from that system I just described. And what you can see in a nutshell is that we can look at the same array, except with a single quantum well in it, a double quantum well in it, a single quantum well quantum dot array, a double dot quantum well array, and then just a quantum well. And here's the quantum well with its broad emission, and then you've got the double and the single quantum dot in the quantum dot array with their narrow emission. This is the arrays actually, which speaks to the organization, and then we can look at lifetimes and so forth. All right, so what's nice about this and why people go this route is because the density of states, when it gets concentrated, becomes these single lines, which means that if the temperature changes, we still will be locked in to these transitions, which means high temperature and sensitivity. Moreover, if you go from quantum wire to quantum dot, you can see it that, as I said, the density of states becomes concentrated, which means that in this case, when we get population inversion, everything has to transit through the high density states that we spoke about in 3D, goes down into these little lines, which means that the threshold, because there's so many at that one point that can essentially oscillate, the threshold current density is extremely low. So, and the modulation bandwidth, because the carriers that sit in the dot, essentially that we're cycling through those states, is very small. So basically they're very fast. So we have fast modulation, narrow line width emitters. Okay, I want to now move on to the last part of this this little presentation, which is the idea of quantum information. So the idea of organizing structure is important because now we're trying to think about systems where systems are interacting. And you know, I talked about templating, but we could also, for example, use mesostructuring. Here's a meso, and you could go back to standard Stratigraph growth. But now, because the meso has essentially the surface strain field will only support one dot or two, depending on its width, we can actually form arrays of dots or bidots if it's wide enough to control our emission and address single dots or a few dots in rows and lines for quantum information systems. And moreover, since the positioning is determined in these systems, we can set them within cavities, and we can use Purcell enhancement to enhance the emission rate. So just very briefly, the selection rules for light with these structures, there's going to be dark states depending on the quantum numbers, and there's going to be allowed states, bright states. And with right and left circularly polarized light, we can access these two allowed states. We'll call them the +1 and the -1 states, owing to the symmetry of the conduction and valence band states that comprise these dots. So the idea here is, can we form entangled photon pairs, i.e. bi-exciton states which recombine to form these, to emit light? And many people have kind of looked at this problem, but the fidelity typically is very poor, something like about 80%, and the quantum efficiency very low, around 10%. So I just want to talk briefly about our work on highly efficient bi-exciton preparation for entangled photon dot, photon generation. In the interest of time, I'm not going to go through all these, but again, you can see fidelities are very low and quantum efficiencies are very low in these cases. And some key issues are these are non-resonant excitation schemes typically, and that means that statistically you're populating any of or all of those n-exciton states, and so you end up automatically having a problem sort of compromising on efficiency and fidelity. The other thing we want to think about is that we want these entangled photons on demand. So one can do optical pumping or electrical pumping, and both schemes are viable schemes. The other thing is we want to control the bi-exciton-exciton separation in order to get efficient generation because of thermal noise. So basic idea is your bi-exciton decays by both electron and hole pairs recombining to emit your two photons. And as written up here, the polarization of the first photon will determine the polarization of the second one within the same decay path. So we have here one decay path, and here we have the second decay path. But because those relaxation channels are indistinguishable, both paths can occur and do occur. And so we have this entangled state, which is shown here. And as far as the bi-exton-exton separation, so we have the energy level spectrum here from ground, exton, bi-exton state. The separation depends on the quantum dot size. So by controlling all the dots and their dispersion, we can, in particular on the smaller side here, the smaller dots, the separation gets larger, and we can stop that crosstalk or effectively keep all the dots moving the same paths. The scheme we came up with was a resonance scheme, and basically we looked at pulse excitation. You can see here the two-color scheme, which is the red and blue scheme, or the blue red scheme, or we also looked at single color excitation, resonant excitation. Let me just cut to the chase here in terms of what happened is that it doesn't actually matter if you use two color, whether you use sequential pulses, that means 1 picosecond pulses, or you use concurrent pulses like a concurrent 1 picosecond pulses. Both cases you get something like 99.7 or 99.1% population transfer. On the other hand, single color, which would be in the state of the art to that point, you end up with only about 95 at best. So clearly this is a nice scheme which you can use to form entangled photon pairs on demand. The on-demand part and how it might work is you can think about this within the context of an integrated photonic circuit, a PIC. And with it, you can think about entangling many such bits and integrating them with the passives, for example, on a silicon integrated photonic circuit. So the idea here is that we'd like to enhance response on those channels using cavities, right? So why the cavities? So in general, light matter interaction in cavities can be dramatically enhanced in a photonic crystal cavity. And the reason is because the light essentially has a very long lifetime in the cavity. It bounces back and forth many times if the Q is sufficiently high. Secondly, by special design of cavity, just go back I'll go forward in a second here. That is, we can control, if we look at the dielectric and we have different spacings within the cavities, we can actually control the modal profile, and we can make, I'll go back here, very concentrated mode profiles, or very small modal volumes, which means that we can enhance the Purcell effect or the emission rate, because the emission rate is going with the Q of the cavity and the modal volume. So our concept is to look at band edge nanowire type cavities where we're using these kind of templates, except we're putting dots in the wires, and we've got Qs as large as almost 1 million and very low modal volumes. So here you can see, as I explained, how we can keep the modal volume down. We can design these cavities so the mode overlaps strongly with the dielectric mode. And you can see the Q by the line width of these peaks, which we've just moved along by filling in a different refractive index medium just to show the shift. And you can see Qs here, which, as I said, around getting towards the 1 million mark. So let me just finish up here. Basically, I want to show that modern growth and processing technology allows us to have unprecedented control over both the dimensions and the materials in quantum dot heterostructures. And with such heterostructures, engineering them appropriately, we can access their unique quantum properties. And I spoke about two types of property. I spoke about properties for traditional applications like the saturable absorber and mid-infrared detector, and also about quantum dot lasers using interband transitions in that case. And I also spoke about emission in terms of quantum information processing and cavities and applying these types of structures I spoke about above. So thank you very much for your attention, and sorry I went on a little bit longer than I had anticipated. Thank you very much.
Thank you, sir, for your valuable presence. So I may invite Dr. Ashwini Kumar Dubey, sir, to present a certificates and sapling.
Oh, thank you.
Yes.
In conclusion, I can say that the time domain and the frequency domain features of EEG and EMG signals well lower.
Sir, am I audible?
Yes, yes, you are.
Yes, I can hear you. Yes. Oh, sorry. Yes.
Yes.
Random forest model,
Sir, can you stop sharing your screen, sir?
Oh, me. Sorry, I didn't realize I was supposed to. Oh,
Yes, yes,
I didn't realize that. Sorry.
yes.
My
Sir,
apologies.
Thank you, sir. Thank you.
Yes, fine, yes. And,
Sorry, I didn't. You should have told me
Okay,
that.
no problem, sir. No problem, sir. It's fine.
Thank you very much indeed. It was a
Thank you, sir.
pleasure
Thank
giving
you,
the talk. Yeah.
thank you. It was really very nice talk.
Yes, sir. 1 second, sir. Yes, sir. We will. Yes, sir.
Congratulations, sir, for delivering such a wonderful talk. I really
Thank you.
appreciate the pain you took here to join this SPIN conference, and I'm really very, humble to see you here. It's really a great pleasure that you have delivered a wonderful talk. Thank you
Thank
so much.
you.
Thank you so much. And next time, definitely we would be inviting you in person.
It'd be lovely to be there in India. That'd be so lovely. Anyway,
That's good.
thank you so much.
Thank you
Thank
so
you.
much. Thank you.
Thank you, sir.
Bye-bye.
Thank you for your presence, sir.
Thank you.
Thank you. Thank you, sir.
Let me just. Should I sign off now? Oh yeah.
Yeah.
Good.
Yep. Yes.
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 Thank
Yes,
you.
sir.
Sorry.
Yeah.
There we go.
Thank
Thank
you.
you, sir.